Hello everybody, welcome back. This video is going to be talking about how to find antiderivatives of the other types of functions we looked at this year, not just polynomials. So the first one up is we have trig functions. So as you remember, hopefully remember, / are reviewing right now, the derivative, so the arrows over on this side of the screen are talking about that. It's supposed to be a circle, not a 6. Remind you how to take the derivative. The derivative of sine is cosine. The derivative of cosine x is negative sine x. The derivative of negative sine x is negative cosine x. And the derivative of negative cosine x takes you back up to sine x, and the cycle continues. So if we are trying to integrate or find the antiderivative, we just move in the opposite direction. So the integral of sine x dx, I go to sine x, I need to move upwards. The integral of sine x dx is going to be negative cosine x plus c. And you can verify that that's correct, because if you take the derivative of negative cosine x, you do in fact get sine x. The other most common trig function you'll be integrating is the derivative of cosine x dx. So I start here. If I integrate, I go back up the chain one step. That is equal to positive sine x plus c. You're definitely most commonly going to be integrating sine and cosine. If you need to integrate negative sine, you can just pull the negative outside of the integral, and you're back to integrating sine, which is this problem. Another common one you'll see is this one. The integral of secant squared x dx. If you remember from our derivative rules, the derivative of tangent is secant squared x, so the integral of secant squared is tan x plus c. So those are the common trig ones. Again, it's really just a matter of thinking back, what was the original function that gave me the derivative I am trying to integrate. I think we've got some examples here. Yep, so we just talked about this. I'm pretty sure that secant x tan x is the derivative of cosecant or something like that. I don't know. We'll talk about it in class. I actually don't know how super important these are. This one you definitely need to know. I think the other ones you can rearrange using just trig relationships, but if you want to have them memorized, that's certainly going to be easiest. Just a quick shout out to the Pythagorean trig identities that are listed here. These are not integration or antiderivative rules. However, we can use these to turn a integral that we don't know how to do into one that we do know how to do. So here's an example down at the bottom of the screen. I don't really know what the integral of tangent squared is, but if I replace tan squared theta plus 1 with secant squared theta, and which I can do because that's a trig identity, tan squared theta plus 1 is the same thing as secant squared theta. It's the second identity up here. So if I just switch tan squared theta to tan squared theta plus 1 to secant squared theta, now I know how to integrate this. Secant squared is the derivative of tangent. So we're back to a problem we know how to do. So the Pythagorean trig identities are not anti-differentiation rules, but they can be useful to help get an integral to a form that we know how to integrate. Okay. Moving on to logs. So if you remember, when we were taking the derivative of logs, the way to take the derivative of a log was to take the derivative of whatever was inside the log function and then divide it by what was inside the log function. So for example, if we had natural log of x to the 5th plus 3x squared, and we want to take the derivative of that, the derivative of this is going to be the derivative of what was inside the log function, so 5x to the 4th plus 6x, all divided by whatever was originally in the function, so x to the 5th plus 3x squared. You could simplify from there, but that's just a review. So when we are trying to go the other way, so when we're trying to reverse the log differentiation process, we are looking for the pattern of derivative over what is the derivative of. So when we're taking an integral, I am trying to spot a pattern that looks like this. All right, so 8x over 4x squared. What's in the numerator is the derivative of what's in the denominator. So this would integrate to natural log of 4x squared plus c. Because remember, when you take the derivative of a log function, you can recognize what was inside the original log function by looking at what's in the denominator. So this pattern is going to be super useful. We are going to be looking for, again, derivative over expression. So here's another example. This one comes up a lot. Cosine x over sine x. This is another way of writing cotangent. So this actually integrates into a log because we have a function in the denominator, sine x. The expression in the numerator is the derivative of what's in the denominator. Cosine x is the derivative of sine x. So actually what this is going to integrate to is natural log of sine of x plus c. That's just a pattern to be looking out for anytime you are trying to integrate a fraction. So the thing that gives away that this might be a log integral is that the integrand, the thing you're trying to integrate, is a fraction. Whenever you see that, you immediately want to think, okay, wait, is the numerator of this fraction the derivative of the denominator? If so, it's going to integrate to a natural log. Moving on to exponentials, remember the pattern for e to the x when we were taking the derivative. When you take the derivative of e to some function, the derivative is the original problem, e to whatever function, times the derivative of that exponent. So just remember, as an example, e to the x to the fourth minus 7x cubed. If we want to take the derivative of that, the derivative would be the original problem, e to the x to the fourth minus 7x cubed, times the derivative of the exponent, so 4x cubed minus 21x squared. So when we are doing integral problems, we are going to be looking for the, if we see an e in the integral, we're going to be looking to see, am I multiplying that e by the derivative of the exponent? And this is the example you see here is a case where we are. 6x is the derivative of 3x squared plus 1. So I have the exact pattern for the derivative of e here. So when I integrate this, I'm just going to get back to e to the 3x squared plus 1. And you can verify that if you take the derivative of this, you do in fact, if you take the derivative of e to the 3x squared plus 1, you do in fact get 6x times e to the 3x squared plus 1. Okay, so I see I've written a helpful note to myself here. So in the past two slides here, I've talked about trying to keep an eye out for the log derivative pattern, where we have derivative of an expression over an expression that will integrate to a log. And here we have an exponential pattern where we have e to an exponent times the derivative of that exponent. Sometimes when we are looking at a problem like this, the integral will almost be the pattern that we need. So I'll write an example. I'm going to revise the problem that's right here to set it up to be where it's almost the pattern. So if this problem had been integral of x e to the 3x squared plus 1 dx. So if I'm looking at this problem, I'm like, okay, I see e to some power times x. I want to check and see, is what I'm multiplying e by the derivative of the exponent here? And I'm like, what a bummer. The derivative of 3x squared plus 1 is 6x, and I'm only multiplying this e by x and not 6x. that sucks for me. But we can do a little bit of math craftery here. So what I'm going to do is I'm just going to recopy the problem. I have x e to the 3x squared plus 1. And I'm going to modify this problem. I'm going to go ahead and just write in that 6 that I need right there in front of the x. So now I have made it so that I am multiplying e times the derivative of the exponent. That's great. However, of course, in math, you're not allowed to just arbitrarily multiply something. I am, however, allowed to multiply an expression by 1. So outside of the integral operator, I'm going to multiply by 1/6. So what I've done here is I've multiplied the original problem by 1. 1/6 times 6 is 1. And in math, you are allowed to multiply anything by 1. It does not change the value of the expression that you're dealing with. So I haven't actually changed the value of this of the answer here. I just changed the way it looks. So I'm just multiplying by 1. 1/6 times 6 is 1. However, I've now modified this integral so that I can do it. It now fits the pattern I need to make the answer. So as we just saw from the previous problem, this integral, the integral of 6x e to the 3x squared plus 1 dx, is equal to e to the 3x squared plus 1. So that part's going to be the same. The only difference is that I now have this 1/6 out front. So we're going to be using this trick where we multiply inside and outside an integral, where we multiply inside and then multiply outside by the reciprocal of that number in order to get integrals to fit a pattern that we recognize. Note that what made this work was that in the original problem, this x that we're multiplying e by, it was raised to the correct power that I needed. I need e to the 3x squared plus 1 to be multiplied by an x to the first. The only reason it was off from the pattern I needed was it was missing just a constant. It needed to be multiplied by 6. That is fixable, as we just saw in this problem. You cannot fix a wrong exponent. So for example, here, if I had e to the x cubed dx, I can't integrate this. We can't. There's just no antiderivative for 3 to the x cubed. In order to get it to look like something I could integrate, I would need it to be e to the x cubed times 3x squared. And I can't do any little math trick to make an x squared appear here. I can multiply by just a number inside and outside the integral, 3 1/3 or whatever, but I can't make variables appear. So since there's not any kind of x squared out in front of here, there's another thing we can do. There is no antiderivative. So as I think I said in class, for derivatives, by the end of the time we were working on derivatives, we could pretty much differentiate any function or combination of functions. There are going to be a lot of integration problems that we just are not going to be able to complete. Integration problems actually have to fit a specific pattern so we can work backwards and figure out what the antiderivative is. Okay, so that pretty much covers the different families of functions. The next few days, we're just going to be doing a ton of practice problems. Like, that's really the best way to get to know these. We're going to be doing practice problems from all the different families of functions, polynomials, exponentials, logs, trig, all that stuff. And really, the best way to be fluent with these is to make sure you review your derivative rules and keep those fresh in your mind so you can spot patterns as you're moving back. The trickier problems we're going to see in this unit are like the ones we just did here, where you have to multiply in and out, but we'll be able to do that. Actually, we'll write one more example problem of those up here for you to try. So this one will be, spoiler alert, a log problem. Okay, so here's the problem. Why don't you go ahead and try it, and the solution will pop up in just a second. All right, so here you go. The numerator was almost the derivative of the denominator. I needed it to be 5x to the 4th, so I multiplied by 5 inside the integral and 1/5 outside. I'll pop up one more example. Okay, here's a trig example for you to try. There's a solution where